Did you know that the average internal combustion engine vehicle contains 35 kilograms or 77 pounds of minerals, of which many fall under the category of critical minerals? Or that the average electric vehicle contains 6 times more minerals than its internal combustion engine counterparts at 210 kilograms or 462 pounds? Critical minerals are not only found in vehicles, but are also important components of vital technologies such as aircraft, wind turbines, batteries, and many more. And with current technological forecasts, their use will only become more widespread and their importance in the global economy more prominent. So, what exactly are critical minerals? According to the United States Geological Survey, a critical mineral is a non fuel mineral or mineral material essential to the economic or national security of the US and which has a supply chain vulnerable to disruption. They are also characterized as serving an essential function in the manufacturing of a product, the absence of which would have a significant consequence for the economy or national security. The 2022 official list by the United States Geological Survey includes 50 mineral commodities considered to be critical. Perhaps you have heard of the terms rare metals and rare earth elements used in the same discussion as critical minerals. It can get a bit confusing. First, both rare earth elements, or REEs, and rare metals are subgroups of critical minerals. REEs include 17 chemical elements in the periodic table consisting of yttrium, scandium, and the 15 elements of the lanthanide series. They're usually divided into light REEs and heavy REEs. Both light and heavy REEs are among the heaviest naturally occurring non radioactive elements and are used in energy and manufacturing technologies. Despite the name, REEs are not rare. They are abundant in the Earth's upper crust, except that there is a lack of concentrated deposits that are economically feasible to mine. Rare metals are a collection of metals used in emerging technologies, of which some of the most known are lithium and cobalt. Unlike REEs, they are not necessarily found in proximity to one another on the periodic table, and they have very distinct chemical properties from each other. Despite their diversity, they are all critically important for the development of specific technologies. Some rare metals can serve as substitutes for certain REEs, and others have completely different and unique applications. High grade ores naturally occur in specific regions within a few countries. For example, cobalt is typically found in copper or nickel ores, and more than 40% of cobalt comes from the Democratic Republic of Congo. I will make future content on the geology, mining, and supply chain of the most traded critical minerals. Overall, the list of critical minerals is not static. Some nations might regard some minerals as critical to their economies while others might not. And countries will also add or exclude elements to their list of critical minerals as their geopolitical and economic importance changes based on the nation's interest. But for the most part, our highly interconnected global economy has led to the list of critical minerals to be fairly uniform. So, why are critical minerals important? As we have seen, critical minerals are important because they are the components of many vital technologies we use today. For example, this can be seen in energy technologies which utilize cobalt and lithium for the production of batteries, or for the aerospace, communications, and defense industries which employ vanadium, cobalt, and erbium to produce fighter jets, drones, tanks, radios, and other combat equipment. More specifically, clean energy technologies employ high amounts of critical minerals, increasing demand as the world transitions to electric mobility and renewable energy. As mentioned earlier, the average internal combustion engine vehicle utilizes approximately 35 kilograms of minerals, predominantly copper and manganese. The average electric vehicle implements close to 210 kilograms of minerals, in addition to a wider variety of them, such as copper, lithium, nickel, manganese, cobalt, graphite, zinc, and other rare earths. These minerals are crucial for battery performance, longevity, and energy density. Similarly, Components of renewable energy technologies, such as in solar power and wind energy, employ greater amounts of critical minerals per megawatt than other energy sources. Natural gas employs around 1,500 kilograms per megawatt of copper and silicon in its energy production. Even higher is the ratio of the weight of critical minerals per megawatt for the production of coal and nuclear energy at 2,500 and 5,000 respectively. These two also employ a wider variety of minerals such as copper, nickel, cobalt, and chromium. Solar photovoltaic generation, on the other hand, averages at 7,000 kilograms per megawatt, making use of high amounts of copper and silicon. Further, onshore and offshore wind generation utilize the highest proportions and variety of critical minerals at 10,000 and 15,000 kilograms per megawatt, respectively, and incorporate copper, nickel, manganese, chromium, molybdenum, zinc, and other REs. This is because critical minerals serve as the components for the magnets used in wind turbines, the cells found in solar panels, and their corresponding electricity networks infrastructure. The demand for these minerals has seen a significant increase in the past decade. The overall demand for rare metals doubled to 125,000 tons per year from 2005 to 2020. Certain minerals have seen significant increases in production, as in the case of lithium, in which global production rose from 18,000 tons in 2009 to almost 90,000 tons in 2019. The introduction of EVs and renewable energy technologies has been a significant contributor to increases in the demand for critical minerals. Electric vehicles are expected to make up almost half of all global light vehicle sales by 2030, and there is an expected doubling of renewable energy generation capacity by 2030 and by almost 300% by 2050. According to a forecast by the International Energy Agency, to meet the goals of the Paris Agreement, the share of the total demand for copper and REEs will have to rise 40% over the next 2 decades. Nickel and cobalt's demand will have to increase 70%, and lithium's demand by 90%. In other metrics, by 2050, wind energy mineral components would need to increase from 190 kilotons per year to 800 kilotons per year. For solar energy, there would have to be a 45,000 kiloton increase of aluminum per year from 2010 levels. And battery storage technology would need to see manganese increase from 12,500 to 40,000 kilotons per year, lithium from 100 to 425 kilotons per year, and cobalt from 90 to 390 kilotons per year, all by 2050 vis-a-vis 2010 levels. In conclusion, what do you think will be the future challenges of transitioning to a clean energy economy based on the information you just heard? Please comment below, as I like to read your opinions. The goal of Future Matrix is to provide data-driven research and consulting on energy through the lens of business, economics, technology, and geopolitics, helping inform your decision-making processes that affect your day-to-day life, whether it be choosing between an internal combustion engine vehicle or an EV as your next car, or deciding in which energy companies to invest.